Hi, I'm John Staples, W6BM. I'm going to give you a demonstration of $20 software-based radio. and come on over here, Steve, and take a look at this screen. I've got on the screen here a audio generator that I needed. I got started in this when I was doing some audio work, and I needed an audio sweep generator. And it turns out that I didn't have one. And so what I did is, using software that's readily available and open source, I put together a audio sweep generator. It's on the computer. Here's what the screen looks like. And I start off right here with these little modules. And these modules all come from this index of hundreds and hundreds of modules. Just open up any one of these guys for example, Fourier analysis. You can get a Fourier transform. You can get some other things. Here's some equalizers up here. If I open up equalizers, you can get some equalizers. Some of these are very complicated. And so what I did is I wanted an audio sweep generator, so I took a sawtooth generator from these, ran it through what is going to turn out to be a frequency controls. So the sawtooth generator gives me a sawtooth signal from, say, 0 to 1 volt. But I want to be able to vary that to give a whole range of audio frequency sweeps. So this goes through some multipliers. It goes into a voltage-controlled oscillator, and then it comes out, goes into the audio of the computer, and also goes into an oscilloscope. So let's make this thing work. And I'm going to turn up the gain of the audio of the computer here. And what you're seeing, let me turn this up so we can hear it a little bit better. I'll hold. Okay. So what are we looking at here? We're looking at, I'm going to change the scope. I'm going to change the scope settings here a little bit. Okay. And over here, I have a slider for the start frequency. We're starting at 20 units times 100 over here. So I'm selecting the start at 2,000 cycles, 20 times 100.
You're selecting the stop at that.
Well, it's a decade. Yeah, oh, maybe. Oh, you're right. It's
ending at 2000.
Scott tells me it's ending at 2000. He's right. I can make it go slower. I can make it go faster. I can turn the volume down. I can turn the volume up. So that actually was kind of cute, and it enabled me to do this audio sweep generator. So I didn't have to go out and buy one. But there's a whole lot of other things that this thing can do, which is kind of amazing. Let's go, for example, there's a number of receivers in here. One of them, and I didn't write. I wrote the audio sweep generator. But here's an interesting one, which is a single sideband receiver using the so-called third method. Does anybody remember what the third method, also called the Weaver method of single sideband generation, is? You actually insert your carrier right in the middle of the audio, about 1.5 kilohertz. And then you do it, and if you do it in quadrature at 0 to 90 degrees, you can actually get a single sideband signal. Now, the phasing method of generating a single sideband signal requires an audio phase shift network that gives you an audio signal that's 90 degrees, the two signals 90 degrees with respect to each other over the whole audio spectrum, and that takes quite an interesting network. I know Dolby has solved that problem. It's actually called a DOME network, D-O-M-E network. This third method of sideband does not require it. It requires two signal generators operating at a specific frequency that give the 90 degrees, but the audio spectrum does not have to go through that. So what these people have done for this demonstration, they actually recorded the actual RF of a single sideband signal off the air, down converted it to a few hundred kilohertz, like IF frequency, and made that into a data file. I'm going to play that data file into the single sideband receiver.
This is a GNU radio single sideband demonstration at 50.3 megahertz, transmitting lower sideband at 50.3 megahertz, lower sideband, 87 LMO.
Now, one of the interesting things is here, of course, if you put the carrier in at a different frequency,
This is a GNU radio single sideband.
you get the duck talk.
50.3 megahertz.
What's the bandwidth, audio bandwidth?
The audio bandwidth on this one, because the question is, what is the audio bandwidth? And because we're doing the carrier at 1.5 kilohertz, the audio bandwidth of the signal that can be produced is from 0 to 3 kilohertz. If you do it at 5 kilohertz, then you've got a 10 kilohertz amount of audio that you can do. So you can do actually high fidelity single sideband using this so-called third or Weaver method. So let's turn that one off. Well, that's a single sideband receiver. We can also do an AM receiver, and we'll just pull that up. It's actually quite simple. And again, somebody recorded a signal off the AM band, down converted it. And how do you detect an AM? You simply square law it, you multiply it by itself. So what we have here, these are the AM signal. In fact, it's as a vector. We convert that complex vector signal to a magnitude, which is our envelope detector, and then simply run it back through our display. The display consists of an oscilloscope, a Fourier transform display, and down here an audio sync, so you can actually hear this in the speaker. And you can see over here, this is the Fourier transform of the detected audio. Here's the carrier. But let me show you the most interesting thing, and that is the spectrum analyzer capability of this thing. Let's open up this one right here, and I've got this one set up to start off at the low end of our FM band, and where that comes in over here, I have this little $20 dongle with this cute little antenna on it, and this is what this is. This device was actually used in Europe when the digital television system started in Europe. So people could put this little $20 dongle, this little antenna, and the HD TV in Europe goes up to about the same range of frequency as it does here, would convert it, and then it would go into their computer, and then they could see the European HD TV on their computer. $20 dongle. And so these became very popular for a lot of other uses. And for example, it makes a very nice spectrum analyzer. And what are we looking at right here? We're actually looking at KQED, 88.5 megahertz right now. Let me pull this up. And
Not very stable. The center of the frequency keeps moving about.
because it's FM. It's FM.
Well,
It's FM.
well, I expect to see it.
Well, let me just do
Right,
this for
yes.
you. Let me just do this for you. I'm going to turn the averaging on, and let me turn the RF gain up a little bit, because there's not much signal coming in here. Because we should also be seeing the iBox sidebands. You can almost see them here, but at home, well, we're in a Faraday cage here. Okay, there we go. Now you start to see the. Could you hold that up? You are starting to see the iBox side. What is iBox? iBox is the digital part of broadcasting. Those guys right there, and they contain the digital part of the signal. And in band on
HD radio.
HD radio. And you can see there's, and in fact I can also turn on persistence. It's actually a really nice scope here. That if I turn the averaging off, you can actually see it's basically a storage scope, and with the persistence here, I can vary the storage time. So there is a lot of peak hold. Another nice feature.
Can you narrow the bandwidth?
Oh, of course I can. And what we're doing that is I'm doing that with these guys here. Here I'm going to expand the bandwidth, or I can come back down. It depends on my sampling rate. Okay.
John, with your peak hold, you could tell if they're over deviating.
Yes, I could. So, well, the peak hold.
Tune into the Stanford.
That's right. So there you are, and it's actually not a bad spectrum analyzer, and I've checked it for linearity. The amplitude scale here is actually quite accurate, and I've got that one set up for sort of narrow band. Let's pull up another one that I've got that actually goes up to a gigahertz, and that's this one right here.
What kind of frequency range can you use?
Yeah, the question is what kind of a range is this? And this module, in fact, I think can go up to nearly 2 gigahertz. I've set it up to go from about 50 megahertz up to about 1 gigahertz. And here we're looking at a larger part of the FM band. And here's 98.9, I guess, right there. In fact, here you can actually look at the cursor and see what the frequency is. Here's your waterfall. And I've got the frequency centered at 100 megahertz here. We can go on up. In fact, we go up and look at the 800 megahertz cell phone frequency band and see if anybody's up there. I think it's about 805.
Show us one of the TV
All right.
8 VSB signals.
Okay, I'll do that. Scott, Gilles wants to see one of the HD TV signals
With the pilot.
with the pilot, and we should certainly be able to see those. And what I'm doing, I'm just hunting around. There's not much signal in this room,
Yeah.
but I think I see a pilot. Can you wave it around and see if you can make the signals go up, or maybe I can find a stronger signal. But what you're seeing here, let me see if I can find a stronger signal here. At my house, the signals just roar in. But
what looks like a noise haystack with a pilot in it.
that's right. Well, here's actually a pilot signal, and what the HD TV signal. I've got about several megahertz, so the signal should look kind of like this. So you should see that this pilot signal is about 300 and some kilohertz off the bottom end of the channel. So that's an HD TV. All it is noise with a pilot in it. But so there you are. That's the demonstration, and what you're looking at is a $20, very decent, and with better antenna, very decent spectrum analyzer that goes up to. There's a question?
Yes. What's the website where we can learn more about these?
The website is, this is all GNU Radio. So if you just go to GNU, GNU Radio, GNUradio.probably.org.
This is all Linux.
And it's all Linux, but it's probably available for any platform. And but the thing is, it's a wonderful way to get started in for free. If you don't have the dongle, it doesn't cost you anything because everything else is totally free. Download with hundreds and hundreds of wonderful modules that you can then just wire up and put together and operate.
The comparison might be to the software-defined radios for $1,500, which is.
Yeah, Scott Robinson says compare this to the $1,500 radios. Of course, those radios have far more capability than this, but this is a way to learn about software-defined radio and just software-defined modules. So if you're not interested in the radio part, you can make yourself audio analyzers. I tried to make myself a network analyzer for audio. It can be done. I was not successful because I'm just barely learning this myself. And so I'm not an expert. I'm just a beginner at this.
Thank you, John.
Software radio.